Hello everyone again. This is lecture 1 part 1 of a new topic called as current electricity. In these we will start with a new discussion today. So let's begin our discussion directly without wasting any time. We will get to know the course outline first and then we will start with the introduction and other portions. So I am Sameer Lavankar. Let's begin our first discussion on current electricity. So here's a course outline for you. So let's not go into further discussions here. First of all, let us start with the introduction so that we can understand what is current electricity, and then we will go on to other features. Some of the things you already know, such as Ohm's law. You would have known Ohm's law in your previous classes directly. In these lectures we will moreover go to different topics like drift of electrons. What is this drift of electrons? What is the resistivity? How are these temperature dependence of resistivity, and so on. So without wasting any time, let's move on to directly introduction only, then we can go on to different topics. Okay, so introduction of current electricity. So in previous chapters, all charges whether free or bound were at rest. So whenever you may have learnt chapters such as electrical charges and potential and so on. So in those, if we need to find out anything such as potential or such as electricity or anything regarding a charge, let us suppose this is that charge I am talking about. Let us this is that charge, either it can be a positive charge or it can be a negative charge. So here everything, when we were talking about, such as we are talking about the potential concept, we are talking about the charge concept, we are talking about the capacitance, anything, for everything the charges were always kept at rest. So this was the initial assumption, if the charges are kept at rest. Now we are moving to another version of it. We are assuming that the charges are moving. What happens when the charges are moving? Is there an induction of something? Is there an induction of magnetism? Is there an induction of current, etc.? So these all are divided into subtopics such as magnetism, something is electricity, something is electromagnetic induction, and so on. So now in this chapter we are talking about, if the charges are moving, what will happen with the charges? Will it produce something? Will there be a voltage difference? Will there be a potential difference across something or else? Okay. So in previous chapter, all charges whether free or bound were at rest. Free as in they are free to move in either direction, such as let us say this is a confined space. In that confined space every charge is allowed to move in any direction, and they are called as free. And bound as in they are constructed that it's your only space is this much, you have to move without any collision, or let us say you have to move only in, let us say, in x and y direction, x direction, y direction, so on. So that is the meaning of bound. Okay. So charges in motion constitute an electric current. So this is the new concept which we got from the current electricity concept, that when these charges which were assumed to be at rest in the previous lectures, only the concept regarding the rest position were being taught about. Here we will talk about if the charges are moving. So now what we got is, if the charges are moving, they constitute an electric current. What is this current we will get to know, but for now what we got is, if these charges are in movement. So let us suppose this is the charge, and if it is moving in this direction, then this is called as, then this produces an electric current. Due to this movement, or due to let us say this movement, or due to let us say this movement, in any movement, let us say it is moving in any direction, then that produces or that induces an electric current. So let me write, due to the movement of charges there is a concept devised called as electric current being produced. Electric current, as the name suggests, because of due to some electric or some electron, some charges, a current is produced. What is this current we will get to know in subsequent slides. Okay. Now such currents as in anything which is produced is defined as electric current here. This electric current is produced when the charges are moving from, let us say, point A to point B. Now such currents occur naturally in many situations. Now we are assuming, or we are taking an examples of some of the electricity concepts which are being evolved in our surroundings only. So lightning is one such phenomena in which charges flow from the clouds to the earth through the atmosphere, sometimes with disastrous results. As you know, you may have heard of many news through which lightning causes deaths of many people, lightning causes injuries to many people. So it causes disastrous result. It is a type of electric current only. It is a phenomena in which charges flow. So as you can see, the charges are being flowed. You can see in this photo here that the charges are being flowing from the clouds to the earth, quite evident. These are the clouds here, these are the earth here, through the atmosphere. The passage is through the atmosphere. So air is used as a passage for the movement of electric current from clouds to earth. So, this is one of the example of electric current being produced or electric current being induced from point A to point B. The flow of charges in lightning is not steady, but now our case is being divided into two parts. Either we are controlling that electric current, we are only assigning that you go from this place to this place in a smooth manner, or I give you full freedom, you can go in any way, you can make branches, etc. So, as you can see, this here is an example of a lightning or an electric current which is not steady, which is not stable, due to which you can see that there are branches moving in another directions, everything is not stable, hence it lead to disastrous result. Now, if you try to confine it, we are saying no, you move in one direction only, this confinement will lead to stabilization of current, and hence it is used in different applications or different appliances, and hence a concept called as current electricity came into picture. Okay. So, the flow of charges in lightning is not steady, but in our everyday life we see many devices where charges flow in a steady manner. Quite evident, we see where charges flow in a steady manner, and that are only the applications of our electric current or current electricity, like water flowing smoothly in a river. So, something we want the charges to move something like this. We want that there should be a smooth flow of electric currents, smooth flow of electrons, smooth flow of charges from point A to point B, such that that thing is stabilized, that thing is not unsteady. We can use it in some appliances. If there is a movement of, let us say, charges in either directions, the wastage will occur. If the wastage occurs, the amount of electricity which we want to produce can't be produced, and hence it is a wastage, and hence it is not our compatible. So, these are the things which we do not want in our everyday life, hence we want that the lightning or the electric charges or the electric current we produce should be of the steady manner. How should we study? The example here provided is of a water flowing smoothly in a river. A water flowing in a river is also due to a potential difference. There is a higher potential difference on, let us say, this direction, and a lower potential difference in, say, let us say, this direction. So, the passage of movement is from higher potential to lower potential. So, there also an unsteady flow can occur, but we are assuming an example of the movement of water only when it is a smooth flow. So, that type of flow is required for our case in lightning, such that current electricity can be put into good use. Okay. So, an example of where the charges flow in a steady manner is a torch and a cell driven clock. So, these are examples of such devices in which a steady manner current charges are being taken place. In this chapter, what we will study? We will study some of the basic laws concerning steady electric currents. So, here the complete concept is to be derived, as in how these electric currents are produced, what are the places where the electricity can be used up to, what is power, what is EMF, what is internal resistance, what are different types of resistance, what are the types in which series resistance can be done, parallel resistance can be done, what is drift velocity, how it is can be compared to different charges, why is it necessary for the drift velocity to come into picture. Then we will study about different applications of current electricity and so on. So, this was a final introduction. Let us move on to next slide now, that is electric current. So, let us now start with a new concept. You already know what is electric current, but let me devise it again so that I can use it in further applications. So, electric current. So, now imagine a small area held normal to the direction of flow of charges. So, let me make a diagram here. So, let us suppose this is that small area we are talking about. Let me write here, this is the small area, held normal to the direction of flow of charges. That means, let us suppose these are the charges. I am assuming charges as small spheres here. Let us suppose these all have positive charges for now. Okay. So, the movement of charges, so the first line says that imagine a small area held normal to direction of flow of charges. Let us say this is the direction of flow of charges. Let us say this is the direction of flow of charges. Let us suppose this is the direction of flow of charges, and we are assuming that this is the small area being talked about here in the first line. Now, both the positive and the negative charges may flow forward and backward across the area. Quite evident, even if the charges are placed here, then also there can be a movement in this direction, and hence and it also does not depend on the charge are positive or negative, anything can flow through this small area. Let us suppose I am assuming these charges to be negative. Okay, so both first second lines are being explained. Now in a given time interval t, let q plus, so q plus subscript, that means that we are assuming charges with positive charge, that is denoted by q plus, and similarly q minus is also written here. Let us denote this by q with a subscript of minus. That means these are the spherical balls here assuming to be of negative charge. Okay. So a given time interval t, let q plus be the net amount, that is forward minus backward, of positive charges that flow in the forward direction across the area. So to explain this all concept, let me just change something. So let us suppose these were the bunch of charges. Let us suppose some of these are positively charged and some of these were negatively charged. Now what does it try to say is, let q plus be the net amount, that is forward minus backward, of positive charges that flow in the forward direction across the area. What does it try to say is, let us suppose there are some charges here also. Let some of them be plus, let some of them be minus. Now what does q plus here say is, let us suppose that this for these charges the direction of propagation is in this direction, and for these charges the direction of propagation is in this direction. Now what it is saying is, let us suppose the amount of charges from this area moving into right hand direction be, let us say 5. So the 5 charges went here and they are placed here. Similarly from this direction, let us suppose there were 3 charges that move from this portion to this portion. So let us say the portion here of amount of charges moving from this portion to this portion was 3. That means the q plus, that is the forward amount of charges movement from point left to right, is equal to 5 minus 3, which is equal to 2. So this is equal to q plus here. So let me iterate it again. So in a given time interval t, let q plus be the net amount, that is forward minus backward, of positive charges that flow in the forward direction across the area. Similarly, so similar concept can be put in for q minus also. Similarly, let q minus be the net amount of negative charges flowing across the area in the forward direction. Now the net amount of charge flowing across the area in the forward direction in the time interval t then is what? So then is equal to q, which is equal to q plus minus q negative. Quite evident, q plus, so our sign convention says that we take the positive charges as plus, negative charges as minus. Therefore there will be some charges which will be which will cancel out each other's properties. Hence let us suppose if you are having 5 positive charges and 3 negative charges, so then the 3 negative charges will cancel the positive 3 positive charges. Hence the total amount of charge which we will have is equal to 2. Now please look into this, why I made this diagram and explain to you, because here q plus refers to the amount of positive charges that is in movement. Let us suppose there were 7 positive charges here totally, only the movement were being done by 5 positive charges. So the current which we will try to derive in the subsequent points will be only and due to those charges which are in movement. There were 2 charges in this direction that were kept at rest. In the first line we understood this concept that electric current is only and only produced due to those charges which are in movement. Therefore these 2 charges, let us suppose these were these 2 charges which were not moving. So these 2 charges were not applicable or not helping in the movement of electric current or in constituting or in producing an electric current. That is why I tried to explain to you that q plus is the amount of charges which is first of all moving from point A to point B. Then next concept was that a total charge moving is, because we need to cancel each other's property. So if the value, I am assuming that let us say the amount of negative charges is less than the amount of positive charges, that means there will be such amount of x amount of q negative charge which will get cancelled. Hence amount of charge which is remaining is equal to q plus minus q minus. Therefore, the formula for electric current is this is proportional to the T first eddy current, and hence the quotient I is equal to Q by T came into picture. So, this is a simple concept that we should know, that electric current is nothing but denoted by I, which is equal to the change in the charges or the difference in the charges of positive and negative charge per unit time. Hence, I is equal to Q by T. So, this is the first formula which we will get. Now, this is defined to be current. So, I is defined to be current, the SI unit of current is amperes, you should know this. So, it is defined to be current across the area in the forward direction. Please make sure this is the current only and only being devised in the forward direction, it is not in the backward direction. Okay. So, this thing is also done. If it turn out to be negative number, then it implies a current in the backward direction. That means what was happening is, let us suppose this value came out to be negative. If this came out to be negative, that it means that the amount of negative charges are greater in this direction than the left direction. That means the current is not in the forward direction, it is moving in the backward direction. That is, the amount of charges being moved from this portion to this portion was much higher than the previous case. So, these were the two cases. So, we knew that if I is positive, that means we are at the assumption of our movement of charges toward the forward direction. Let me assume the forward direction as this portion was correct. If it comes out to be negative, that means that means our assumption is wrong. Hence the current is in the backward direction. So, this is the first consumption. This is the first thing which we understood, that I is equal to small q by t, or we can also write it as I is equal to delta q by t. Okay, so this is the formula sheet also being updated right by side here. So, everything which I will try to understand you in the subsequent slides, I will try to keep on updating it, so that finally you will get a complete sheet such that you can remember those formula for your exams. Okay. So, currents are not always steady, and hence more generally we define the current as follows. So, now a general definition of current will be defined here. So, let delta q be the net charge flowing across a cross section of a conductor. So, let us suppose I make a conductor in this fashion. Let delta q be the net charge flowing across the cross section. So, this is the cross section here, or let us suppose any point here to be cross section. Let us say complete area, anywhere can be the cross section. So, let us suppose I am writing here, so that I do not destroy the diagram, cross section. Okay. So, this is the cross section, let delta q the charge, that means the complete charge, let there be a bunch of charges here, let there be a bunch of charges here. So, when these charges were being subtracted from the previous later part, then the amount of charges which we got is denoted by delta q. So, this is the concept being talked about here, delta q, and please let me write here, this is the conductor being talked about here. Okay. So, let delta q be the net charge flowing across a cross section of a conductor during the time interval delta t. That means, at some time t the amount of charges were here, and we are assuming that at some time delta t the amount of charges moved from this portion to this portion, the amount of charges is equal to delta q, and hence at time t is equal to t plus delta t, we took the charges here and we found out the amount delta q also, and delta t is already known to us because that was being calculated, let us say using a stopwatch. Okay. Then the current at time t across the cross section of the conductor is defined as the value of the ratio of delta q to delta t, that is delta q by delta t, in the limit delta t tending to 0. Hence, current is defined in this form, mathematical form, that is what it was saying, that is delta q by delta t. If we need to find out the instantaneous value, then we will just put limit here, limit delta t tends to 0. And hence this is defined as nothing but called as your current. As it is a function of time, it is written as I of t. So, this is the same formula which is being devised here. The SI unit is ampere. So, this is the thing I already explained to you, and you may already know that current is being devised using amperes. It is denoted by this sign A here. An ampere is defined through magnetic effects of current, and ampere is typically of the order of magnitude of current in domestic appliances. An average lightning carries currents of the order of tens of thousands of amperes. So, this should be known that the amount of lightning, so the concept we understood in the introduction chapter, there were tens of thousands, that means 10 to the power 4, 10 to the power 6 amount of current is being involved in lightnings, And similarly on the other hand, if we go to the extreme portion, these were the two extremes. The other extreme is current in our nerves, in our muscular system is of the order 10 to the power minus 3, that is microamperes. So in this case it is 10 to the power minus 3 amperes. So let me stop it here for our this lecture. So in this lecture we understood the concept of introduction of current electricity, what were the differences from the electric charges and potential concept which we understood in the previous lecture. If you have studied the electric charges concept, here we are studying about the current electricity in which the charges are moving from point A to point B. So, to do that movement from point A to point B, it constitutes an electric current. Then we understood the concept of formula of electric current, that is I is equal to Q by T. If we need to generalize it, then it is I is limit tending delta T tending to 0 delta Q by delta T, where delta Q is the amount of charges moving across or through a conductor from point A to point B in some time delta T. So, let me stop it here only. Thank you.